This is lesson 10, optimization. We'll visit the other major category of word problems from Calc A. We saw related rates in the last video. Optimization problems comes from the word optimize, to make something the best it can be. Optimization is actually one of the most common uses of calculus in application, right? We're trying to maximize the size of or here, maximize the volume of a shipping container, minimum amount of material to produce a soda can. There's actually a link about that that's pretty interesting. So yeah, optimization is pretty important. And usually, at least for us, what we're trying to optimize is essentially finding a max or min. Okay, we'll start with a simple example. Simple, silly example. Here is an equation. C of X, which represents the production cost for a dog hoodie in terms of number of hoodies. So this is not uncommon where in production, the larger the batch of items produced, you can sometimes reduce the costs involved. So here the factory owner wants to minimize the average production cost, how many hoodies should be produced. This one's fairly simple because we already have cost in terms of the variable X. So we can simply find the rate of change of C with respect to X. Okay, we're trying to find max or min, so we set that equal to 0. And 3 pops out of it. Now, it's really tempting to just say, okay, we're done with the problem, the answer is 3, but really and truly, you should confirm that this 3 does actually correspond to a minimum in this case. Okay, we know that numbers that pop out of this procedure here, critical numbers, are candidates for max or min. We don't know which it is yet. It could be none at all. So I investigated, I have my little number line here. I do see a sign change in dCdx from negative to positive at 3. So yeah, we do actually have a minimum at x equals 3 because dCdx changes from negative to positive. Okay, I went further to find the actual production cost, but you don't have to do that because the problem doesn't ask you to, but I'm just plugging the 3 back in to the original equation. Now that was a simple one. Many optimization problems are more challenging because they're going to involve more than 2 variables. So in those cases, I've got some steps that you want to follow. Number 1, identify all the quantities involved. Make sure you draw a picture if it's going to help. And then immediately following that, you want to write what I call a primary equation. This is going to be the equation for the actual quantity that you're trying to maximize or minimize. Now, with many variables involved, you might sometimes have to use a secondary equation. Secondary equation, we're not actually going to do any calculus on it. It's just there to possibly help us see the relationship between these many variables and hopefully eliminate some of them. We should also be thinking about the domain. Some of these word problem contexts, for example, like if a negative number popped up as a candidate and we were measuring lengths of objects, that wouldn't make sense in the context. So think about domain restrictions of that. Finally, you do use calculus to essentially find a min or max. All right. 10.2. We need to find 2 positive numbers such that the sum of the first number plus twice the second number is 100. The product of the original numbers is a max. Okay, so we're trying to maximize product. That's our primary equation. I used P for product, and if I'm calling my 2 numbers X and Y, here's one way you could write out that equation. P equals X times Y. But we'd like to simplify this down to have 1 less variable. So we're looking for a secondary equation. And if there's any other given information that you haven't used yet, that's probably where you're looking for the secondary equation. X plus 2y equals 100. I'm doing algebra here to solve for X with the intent of removing X from my primary equation. Everything now is P in terms of Y. That's going to make our lives easier. I multiplied out just a little bit further, and now I'm ready for the calculus. I'm differentiating P with respect to Y. Those aren't the traditional variables you might be used to, but That's what we're using here. dp dy equals 100 minus 4y. I'm setting that equal to 0, looking for candidates for a max. I get a 25. I don't yet know if that's a maximum until I do some further analysis. I've got my number chart with p prime switching from positive to negative at 25. So here's me justifying, and we are done. Well, actually, we're not quite done, because our goal is to find the two positive numbers. As of yet, we've only found one of them. So make sure that you read directions and give everything provided. We can use our secondary equation. Now that we know what y is, we can plug that in to figure out what x had to be. So my numbers were 25 and 50. Okay, example 10.3. Farmer is fencing in a pasture adjacent to a river. You can see from my picture here, the impact of that is that the fencing is really only 3 sides of a rectangle. The river itself is making up one of the borders. Pasture needs 180,000 square meters to provide enough grass. What dimensions would require least amount of fencing? There's my clue that this is an optimization problem. We're looking for a minimum amount of fencing. The amount of fencing, it's kind of like a perimeter problem. Not a full rectangle, but I could say, if you go off the same labeling I've used in my picture, we could say perimeter P equals length plus 2 copies of the width, okay? But I'd like to remove one of these variables if possible. So I'm looking for other information that might point to a secondary equation. And it's this bit about the square meters, that's area. Length times width is going to be 180,000, okay? So length then is 180,000 over W. I make a substitution then over here. And now we're ready for the calculus step. dP dW. And I'm differentiating the right side in terms of W as well. And once I have that, we're setting it to 0. Okay. Algebra to solve that out. W would have to be positive here. Really, you're getting 2 answers, but we only want the positive one. And yes, we should also be checking to confirm that we have a minimum there. I've got my sign chart. I've got my justification in words. Now that we have the width figured out, we also need to find the length, because we're trying to find the dimensions plural. That's a length and a width in 2 dimensions, right? So again, I'm plugging back into my secondary equation here to figure out that the length would be 600. So we've got a 600 by 300 meter pasture. Every word problem is different. Okay, I'd love to tell you there's only 2 or 3 types and just memorize them, but that's just not how it works. You might even see problems that are similar to problems you've seen before, but end up not exactly being the same thing. In fact, I'm thinking about putting an open top box problem on our test. And I'm actually a little worried people might see it and think, oh, it's the same as this one from the video, but I think it's going to be one that's a little different. Okay, so just because we're seeing this next example here, we don't want to assume even that every open top box problem is the same. You have to read the given information really carefully and decide how to proceed. But for this problem, we've got an open top rectangular box. We're starting with a flat piece of cardboard. And of course, you can make an open box by cutting squares of the same size out of each of the corners of a single rectangular piece of cardboard. Okay, so that's what we're going to do here. We just want to know how big do those squares have to be? And more generally, what are all the dimensions of the box going to be if we want to maximize the largest possible volume of this open top box? So I've got a diagram here. Imagine taking a full rectangle and cutting out a square in every corner. I don't yet know the lengths of those square dimensions. I'm going to call that my X. And what I know then is that this middle piece that I'm highlighting, okay, originally it was 10 inches across, but if I'm looking at just this middle piece, if we're subtracting or accounting for an x and an x on either side. This dimension here, which is going to end up being one of the dimensions of the base of the box, would have to be 10 minus 2x. Similarly, this piece here, if we account for an x and an x above and below it, this piece must be 16 minus 2x. Okay. If you can imagine folding up these four outer flaps, hopefully you can visualize this open top box such that its length, width, and height are represented by the 16 minus 2x, the 10 minus 2x, and the x. And that's how I end up with my primary equation for volume here. Length times width times height. And you might multiply that all out, okay? What's nice about this problem is we only have one variable on the right side. So this is a case where we didn't need a secondary equation. Just multiply this stuff out. When you get it to a nice form for differentiation, go ahead and do so. Set your result equal to 0. We're back in algebra class now. Looks like I'm breaking up that middle term to do a factor by grouping technique, but you can factor however you're comfortable. But everyone should be able to solve this out. You get two possible answers for x. So we'll check out both of them. Turns out only one of those corresponds to a max. I'm looking at the sign change from plus to minus in dv/dx that occurs at x equals 2. We actually have a minimum at the 23rds, okay? So yeah, we're gonna go with 2, okay? And then, you know, again, we want all the dimensions listed. So 2 is one of our dimensions, that's the height. Plug back in to these other two pieces to figure out the 6 and the 12 as the width and the length. All right, moving right along. 10.5, this time we've got a rectangle bounded by the x-axis. Whoops, there's my x-axis in my diagram. And a semicircle. If you're not familiar with the equation of a semicircle, it's worth memorizing. It comes up quite a bit in this course. Anytime you see y equaling a square root of a constant minus x squared, you've got the top half of a semicircle. If there were a negative sign in front of that radical, it would be the bottom half. And of course, plus or minus the radical would be the full circle. That's no longer a function, but that's what it would be. All right, so here's my setup. And we want to maximize the area of that rectangle. Therefore, we need an equation for area. I'm going to zoom in a little bit here. Again, I'm treating this horizontal line as an x-axis. I essentially chose to draw this so that the center of the semicircle was at 0, 0. So you can imagine this vertical line in the background is actually the y-axis. Okay, and I'm just noting that if I choose to move a certain distance on the positive x-axis, we'll call this distance x, then the full length of my rectangle would be 2x, and the height would be exactly equal to the value of the semicircle function at the x value we've chosen. So quite literally, the height would be square root of 25 minus x squared. So here's my formula for area. I'm taking my length of 2x times my height of 25 minus x squared to the 1/2. I skipped over the part where I actually write length times height or length times width, so I don't need any secondary equation. Everything is already in terms of x. Looks like we are going to need some product rule on that derivative. That's kind of a tricky one with the radical, but it's doable. And then we're solving this thing for x. It's not as bad as it looks. One of these terms, you know, once we've set this to 0, one of the terms goes to the other side. You could then multiply that radical back to the left. In doing so, we remove radicals altogether. Trust me, if you guys have passed algebra, you should be able to get here, no problem. Again, though, we want x to be positive because we decided that we were going in the positive direction of the x-axis. Double check your value to confirm that we have an actual maximum there, but it does work out. And let's see, it does say find the length and width. So after I find my x value here and check it, I need to plug back into the function for y to give myself the height or width or whatever we're calling it for the rectangle. It turns out it's also 5 over root 2. Okay, one last example. This one, we've got another rectangular sheet. Perimeter is locked in. We need to figure out the X and Y dimensions if we're going to roll this into a cylinder. Okay, so imagine taking what's originally a rectangle sheet and sort of rolling it. Imagine like rolling a piece of paper into a tube. Um, so that X dimension is actually corresponding to what's going to be the circumference of that cylinder. So we know X is equal to 2 pi r. Y is representative of the height. You could even solve for r, which I'm going to do because we want to be working in terms of X and Y according to the prompt. Okay, so maximize volume. Here's the conventional geometric volume formula for a cylinder. But immediately I want to turn this into X's and Y's. So I'll use the replacements that we worked out over here. R becomes X over 2Y, H and Y are one and the same. Okay. Furthermore, I'm going to try and get rid of this Y because I do have some secondary information to make a secondary equation involving perimeter, which shows us the relationship between Y and X. I can then plug in. So now we're in good shape because we only have two variables, V and X. Clean this thing up a bit if you like, and then go ahead with your derivatives, dV dx. Set it equal to 0. Solve it out. We got a couple possible answers, one of which doesn't really make sense in context. We can't have the width of our sheet be 0 and have a meaningful rectangular sheet. So 12 is the answer that we're interested in. Double check it, write a sentence to confirm. Once we're confirmed, we do want to plug back into our secondary equation to also figure out what Y was. And now we've got the dimensions, X and Y, that give us the largest volume, turning that rectangular sheet into a cylinder. As you can see, we're skipping this last example, pretty similar to something that was already in there, I think. So yeah, that's the end of the video. Let me know if you have any questions. Yeah, thanks for watching.